Right. Okay. All right. Okay. Good afternoon, all. We'll start. It seems still others are joining, right? But we'll start. How about my audio and video? How about the audio and video? Is it clear enough? Is everything good? Clear. Okay. Thank you. Okay, we'll start. So, as we planned, we are starting angular momentum today, right? And the today's plan is we'll be starting angular momentum, and as well we are going to finish off everything about angular momentum by the end of today, right? And the next new lesson we are starting next week is circular motion, right? So therefore, today we have quite a few things to do, quite a lot to do, right? So therefore, we'll be doing things a little bit faster because my plan is to finish all the things regarding angular momentum by today itself, by this single day itself, right? Okay, then let's start. Take down the heading as angular momentum. Angular momentum. Angular momentum. Right. 1 second. Okay. Right. So you can get the route using the link that I have put to the channel, right? Or else if you are on YouTube, you can get the route through the link that is pinned in the live chat, right? So you can get the route on channel or YT live chat. On channel or YT live chat. Okay, let's start. Right. Okay, listen. The plans for the month and today we'll be finishing angular momentum by this single class itself, and next week we'll be starting circular motion, and main lesson we are going to cover during the month of February is circular motion, right? Main lesson we are going to cover during the month of February is circular motion, and on today itself we'll be having the fourth day of S2A discussion, right? Fourth day of S2A discussion, and that will be a continuation of vectors and force equilibrium questions we discussed last week, right? And in the reverse class, we are starting elasticity, right? Those are the things coming up during the month for you, especially the main lesson will be circular motion that we'll be covering during the month, right? So today itself, we'll be covering the full lesson of angular momentum here with the questions and everything, right? And next week, we can get a fresh start to circular motion. All right, angular momentum. So before angular momentum, tell me what is linear momentum as an equation. Tell me what is linear momentum as an equation. What is linear momentum as an equation before angular momentum? Linear momentum. What is linear momentum as an equation? Huh? What is linear momentum as an equation? Now, if you are on YouTube also, you can put your responses to the live chat, right? If you are on YouTube also, you can put your responses to the live chat. Right? Linear momentum. Linear momentum is mv. Linear momentum is mv. Right? Now, if I compare this with angular momentum, look at the board. If I compare this with angular momentum, about these conversions we discussed on the first day of rotational motion or the angular motion, right? About the conversions we have discussed on the first day, right? If I recall again, if angular momentum is p, right? Instead of m, we have I here in rotational motion, in angular motion. Instead of v, we have omega here, right? So therefore, angular momentum is defined as I omega. Angular momentum is defined as I omega. P equals I omega, where I is moment of inertia, right? Where I is moment of inertia. 1 second. And omega is angular momentum. Sorry, omega is angular velocity, and p is angular momentum, right? Now let's compare these two starting from here, because for the definitions and the applications, users and everything, this comparison is very much important when we are moving on, right? Okay, take this down, take down both. This is linear momentum. Take down both, and we'll be introducing both terms. P linear momentum, and introduce terms P linear momentum, M mass, V linear velocity, linear velocity, linear velocity, right? And here, this side, P is angular momentum. P is angular momentum. And I, moment of inertia, moment of inertia, and omega, angular velocity. Angular velocity. Take it down. Linear momentum and angular momentum. Right? And find units and dimensions of angular momentum quickly. Find units and dimensions of angular momentum. Find units and dimensions of angular momentum. Find units and dimensions of angular momentum. You can send your answers. Okay, any answers? Units and dimensions. Units and dimensions of angular momentum. So about I, we know I is mr squared. I is mr squared. So whatever the coefficient it comes in front, coefficient is a number. So therefore, as a dimension, we have mr squared in I. Right? We have mr squared in I. Right? So therefore, you can write this as units of I into units of omega. Units of I can be written as units of m times units of r squared omega. Units of mass is kilograms, r meters, right? kgm squared, omega r radius minus 1 radius per second. Right? This is a unit of angular momentum. For the dimensions of I times dimensions of omega. Dimensions of I is m times dimensions of r squared into dimensions of omega. Right? Mass is capital M, r squared is L squared, dimensions of omega is t minus 1. We have proved already. Right? ml squared t minus 1. ml squared t minus 1. ml squared t minus 1. Right? Okay, let's move on. As the next heading, write down moment of inertia. Next heading, moment of inertia. Moment of inertia. Moment of inertia. Moment of inertia. Okay, look at the board. Look at the board. Moment of inertia. So let's assume this is a random object and the object is going to rotate around this axis. Object is going to rotate around this axis, right? So let's label this axis as y. The object is going to rotate around y axis, and we are going to split the mass of the object, total mass of the object, to n number of small particles, like this, right? So let's say these particles are m1 small particles, m2, m3, m4, likewise it goes. Small particles, tiny particles. When we consider a particle, right, center of mass of the particle is also on that same point itself, right? And let's consider perpendicular distances to each as r1, r2, r3, r4, and so on, likewise, right? Likewise. Now, since moment of inertia can be written as mr squared, listen, since moment of inertia can be written as mr squared, right? mr squared. Now, moment of inertia due to each particle can be written as their respective m into r squared, right? Respective m into r squared. Then, if I need the total moment of inertia of this system, right, I total should be, right, total of moment of inertia should be the addition of sum of the moment of inertia of all particles, right? So therefore, I total is given by I total. Look at here. I total is given by, right, moment of inertia of each particle, like I1 plus I2 plus I3 plus I4 plus up to last one, let's say IN, up to IN. Right, let's say this is done for n number of particles. Last one is Mn. For that, the distance is Rn, like this. Right. Then I total can be written as I1 is M1 R1 squared. I1 is M1 R1 squared. I2 is M2 R2 squared. I3 is M3 R3 squared. I4 is M4 R4 squared plus this last one is Mn. Last one is Mn Rn Mn Rn squared. Right? So this is a series now. This is a series. This is a series. Since this is a series, now we are going to narrow down. We are going to shorten this series and write hereafter. Right? So about shortening a series, we are using the sigma notation. Sigma notation. I think you have used the notation in O levels also. The sigma notation. Right? So I total can be written using sigma notation. Sigma means addition. Addition. And here we put the sign of sigma. Sorry, we put the limit of sigma. Right? Now the sign limit of sigma. Limit means from which one to which we have to take the addition. That's the idea. Now here as a common term we can write mi ri squared. No? See, now once I wrote this you will understand. From I equals 1 to n. The idea here is, see, the idea here is take the addition of mi ri squared. Take the addition of mi ri squared. The term when I varies from 1 to n, then first term is m1 r1 squared. When I equals 2, m2 r2 squared. When I equals 3, m3 r3 squared. So and goes, and the last term is when I equals n, mn rn squared. Right? As another example, if you need some further understanding, say you need to take the addition of 1 plus 2 plus 3 plus 4 plus 5. This can be written using sigma as I equals 1 to 5, right? As xi, sorry, as I, something like this. Got it? Something like this. Say you need to take the addition of the squared values of a number, 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. This can be written as when I equals from I equals 1 to 5 I squared. Something like that. This is called the sigma notation. Sigma notation. So we use the same thing here. Then this series comes when sigma I varies from 1 to n, mi squared. Sigma means addition. Right? And limits of sigma is where to start and where to end your series. Right? Then with that, this whole series comes, and that is shortened using this. Moment of inertia is defined as, listen, moment of inertia of the object is defined as I total is defined as sigma mi ri squared from 1 to n. Right? Once this is simplified, it comes along with, listen, it comes along with a coefficient. Right? And to simplify this hereafter, we need another mathematical simplification called integration. So therefore, finding moment of inertia of objects is not here in A-level physics, right? But if we have an external axis like this, always you can write moment of inertia as mr squared, right? For m1 r1 squared. So likewise, if there is an external axis, always you can write it using mr squared, right? But for one axis, always a coefficient comes. That coefficient is a result of mathematical integration, right? That is called integration. So therefore, since there is a combined maths part, we don't have the integration part here. In such cases, you will be offered the moment of inertia. But if the object rotates around an external axis, it won't be given, because about external axis, you can always write it as mr squared. But if there is an internal axis, internal in the sense on axis, always moment of inertia is given, right? Okay, start from here and take it down. This is an example to you to see this sigma notations if needed, right? It is up to you whether it's taking down or not, right? Otherwise, what I need is from here to here. Right down. Then I go to pray. Yeah, you can leave and come back in 5 or 10 minutes. You can come back. Finished? Okay, write down below in red. Write down below in red. This is the definition of moment of inertia, right? So write this definition in red. Write this definition in red. This is the definition of moment of inertia. This is the definition of moment of inertia. Write down. If an object is made of, write down. If an object is made of, if an object is made of, if an object is made of particles, if an object is made of particles, write this way: M1, M2, M3, M4, put some dots up to Mn like this. Mn. And perpendicular distances and perpendicular distances from axis of rotation and perpendicular distances from axis of rotation and perpendicular distances from axis of rotation, perpendicular distances from axis of rotation are like this: R1, R2, R3, R4, put some dots, Rn. Respectively. Total moment of inertia, put a comma, respectively, put a comma and write down, put a comma and keep writing. Total moment of inertia around the axis, total moment of inertia around the axis, can be written as, total moment of inertia around the axis can be written as, total moment of inertia around the axis can be written as like this: I equals sigma mi ri squared from I equals 1 to n. Write this down. Okay, so find units and dimensions of moment of inertia quickly. Find units and dimensions of moment of inertia. Units and dimensions of moment of inertia. Find units and dimensions of moment of inertia. Find units and dimensions of moment of inertia. Right? I is mr squared, then units of m into units of r squared, it gives kg m squared. Dimensions of mass into dimensions of r squared, right? That is ml squared. ml squared. Fine. Write down below with a red pen. Write down below with a red pen. Put an asterisk mark. Write down below with a red pen. Put an asterisk mark and write down. Put an asterisk mark and write down. Inertia of an object is. Inertia of an object is. Inertia. Inertia of an object is. Inertia of an object is. Inertia of an object is. Inertia of an object is the reluctancy. The reluctancy. The reluctancy. The reluctancy of an object to. The reluctancy of an object to. Reluctancy of an object to change its behavior of motion. Reluctancy of an object to change its behavior of motion. Change its behavior of motion. Change its behavior of motion. Right. As an example, it is like this. Listen, objects which are moving are always trying to be moving. Right. They have a reluctancy to come to rest. The objects which are moving. Right. Objects which are at rest are always trying to be at rest, right? They're trying to be at rest always. They have a reluctancy to move, right? So either way, any change of a state, there's a reluctancy of an object to do any change of the state of the motion, behavior of the motion. That is called inertia. That is called inertia, right? Within brackets, write down, within brackets, moving objects are reluctant to, within brackets, write down, moving objects are reluctant to. Moving objects are reluctant to stop, and non-moving objects are reluctant to move, and non-moving objects are reluctant to move, and non-moving objects are reluctant to move. Non-moving objects are reluctant to move. Next point, second point, keep using the red pen. Second asterisk mark, write down. Moment of inertia Moment of inertia measures that reluctancy of an object. Moment of inertia measures that reluctancy of an object. Right. Now, if I break this down further, it is like this now. Listen. If I break this down further, now we know I equals mr squared, general equation of moment of inertia. I equals mr squared. But this is valid only when, right? Only if object rotates, around an external axis. Only if object rotates around an external axis. Right? So therefore, when we are using this for internal axis, we do a small change, and we are going to use this idea. We can't find the coefficient anyway. You can't find the coefficient anyway, right? Here there will be a coefficient that we can't find, right? So in that case, what we do is, we are using this R as distance to center of mass distribution. Right? If you are writing this for an internal axis, so therefore it is never going to be the radius. That is not the radius. That is distance to mass distribution. Right? Now, about the applications here in this part, we will be discussing today itself at the latter part. Right? So initially we will be starting off with angular momentum, and from this one there are specific types of applications are coming. I'll be discussing such applications towards the latter part of the lesson. Right. So first write this down. Only the first one. Write this down. Only if object rotates around an external axis, and highlight this external axis. Right, write down. Only if object rotates around an external axis. Write down below. With an asterisk mark. Write down. If the object rotates around its own axis, if the object rotates around its own axis, around its own axis, a coefficient comes in front of mr squared. A coefficient comes in front of mr squared. Above equation is used as follows. 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 For such scenarios, above equation is used as follows. For such scenarios. For such scenarios. Right. Look at here. Now in that case, right? In that case, this is not just a perpendicular distance, right? In that case, I is moment of inertia as usual, right? The change is with R. M is mass, and R is very much important. R is very much important. R is distance to, R is distance to center of mass distribution, right? Take it down. I will explain an example here again. See, as an example, let's say we have a disk here. This is a disk, right? This is a disk, right? Now mass is distributed from here to, mass is distributed from here to here. No? Look at the board. Mass is distributed from here to here. Then center of mass distribution is somewhere around the center, around the middle of this line, right? Something like this. And let's say, on the other hand, I have a ring type object like this, a ring type object like this of the same radius, a ring type object. Now here mass is distributed only in this part. That's a ring type object, only in this part. Now mass distributes from here to here only, right? Mass distributes from, look at this line, here to here only. Then somewhere around the middle of that line, its center of mass distribution is located. Now let's say in this case it is case A, scenario A, and this is scenario B, and this is RA, and this is RB, right? Now can you see, since I equals mr squared, IA is, right, MA RA squared, and IB is, right, MB RB. Let's consider equal masses for your understanding. Okay, if I consider equal masses, say this is also M, this is also M. Now it's easy to compare. No? RB squared. For sure, we can say IB is greater than IA. So likewise, we can make decisions. Based on this what we know, right? Distance to center of mass distribution. So there are more examples coming up in the latter part, and we'll be doing some of the applications like about times, about velocities, about rotational speeds, different things in the coming part, right? Now for now, knowing up to this point is enough, right? For now, by the end of today, we will discuss everything, right? So after taking this down, take down this example as well. After taking down, take down the example as well. Could you explain again? This one. Center of gravity. Yeah, center of gravity is at the center. Center of mass distribution is at the middle of the mass distribution. Mass distribution is from here to here. Mass distribution is from here to here on this line. Here the mass is distributed from here to here from the center. And at this one, mass is distributed from only from here to here. Right? Center of mass distribution is located around the center, around the middle line of the mass distribution through this axis, through the rotational axis. Right? So this is close to R over 2. This is in this region for sure, that is greater than R over 2. Right, take it down and raise if any other questions. No, totally different. Center of mass and center of gravity are totally different. Totally different. Center of gravity of this one is at the center. Center of gravity of this one is also at the center. And in both cases, center of masses are also at the center. But center of mass distribution are different. Totally different. So if they are same, we would be using the same term, right, without any other complexity. But they are not the same. They are totally different. Take it down. Understood. Okay, good. Right. Let's move on. Okay, finished. Now let's get back to where we started the discussion. Now let's get back to where we started the discussion. Look at here. All right. Look at here. Right. So we knew that angular momentum can be written as I omega. We knew that angular momentum can be written as I omega. Right. But we know, but moment of inertia. Don't write, look at the board. But moment of inertia around an external axis. Moment of inertia around an external axis can be written as about an external axis only, about external axis can be written as I equals mr squared. No, I equals mr squared. No. Now if I use that idea here, see what happens. Then from above P equals I omega. But since I equals mr squared, see, since I equals mr squared, right, P can be written as mr squared omega, right? And in addition, we know omega is V over V equals R omega. So omega is V over. Omega is V over. Then mr squared for omega, we can write V over 1 R2, R cancels. Right? Right? And it comes to mv times R. P equals mv times R. Here mv is linear momentum. Right? mv is something we already know. mv is linear momentum. Now linear momentum into a perpendicular distance has come. Linear momentum into a perpendicular distance has come. So this is called moment of linear momentum. Right? This is called moment of linear momentum. Moment of linear momentum, because force moment is force into perpendicular distance. Now this is linear momentum into perpendicular distance, so it should be moment of linear momentum, right? So one additional thing, as the general equation we know P equals I omega, angular momentum is I omega, but in addition we can rearrange I omega using linear momentum like this. It comes as moment of linear momentum Now it is like angular momentum equals moment of linear momentum. So this is the relationship between angular momentum and linear momentum. There's a relationship. The relationship is here, right? This is how we can prove it. Okay, start from here. Take it down up to this point. What do you mean by internal and external axis? First day of angular motion. What do they are on the first day, starting day of angular motion. Everything is connected from the beginning. Everything is connected from the beginning. Take it down from here to here. Take it down. Example. If this rotates about an internal axis itself, the rotation is like this. If there is an external axis, the rotation is like this. Right. So after this, introduce these terms. Introduce these terms from this one. Introduce these terms. Introduce this way: m mass, v linear velocity, v linear velocity, and r perpendicular distance. R perpendicular distance. R perpendicular distance. Introduce terms: m mass, v linear velocity, r perpendicular distance. Right. Now, if I summarize what we learned up to this point, listen. If I summarize what we have learned up to this point, is this. Right. I'll be erasing this part. If I summarize what we have learned up to this point, it is this. Look at here. Angular momentum. Right. E equals angular momentum. Can also be written as what? Moment of linear momentum. Can also be written as moment of linear momentum. As equations, if I write this, P equals, this is I omega, right? And this is MVL, right? Take this down and highlight. Take this down and highlight. Right, this is the summary up to here. P equals angular momentum equals moment of linear momentum, right? Angular momentum is I omega, or it can also be written as moment of linear momentum mv into L. mv times L, mv into L. right? As the next heading, write down. We are moving on to the main part, the core area of the lesson, core area. Write down. Law of conservation of angular momentum. 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 Right. Listen. Now this is also very much comparative to linear momentum. Very much comparative to linear momentum. See. Now this side I'll be writing the law of conservation of linear momentum for the comparison purpose. Right? Linear momentum for the comparison purpose. And this side I'll be writing angular momentum for the comparison. Right. About linear momentum, we have discussed like 3-4 months back, like 3 months back. Right? Linear momentum is proved like this. Right? We know F equals ma. No? When F equals ma, A can be written as V minus U over T. Then it comes to F equals mv minus mu over T. Right? Linear momentum is when F equals 0. See, this happens when F equals 0. When external unbalanced force is 0. What happens is 0 equals mv minus mu, which means mu equals mv. Mu equals mv means, right, total initial linear momentum, right? Total initial linear momentum. See, total initial linear momentum equals total final linear momentum. No? So here what happens is the exact comparative one. As F equals ma, what we have here in angular motion is torque equals I alpha. Right? Torque equals I alpha. So where alpha can be expanded as omega 2 minus omega 1 over T. Right? Which means torque equals I omega 2 minus I omega 1 over T. Right? Now this is when torque equals 0. This is when torque equals 0. Now what happens is 0 equals I omega 2 minus I omega 1. I omega is representing angular momentum. So I omega 1 is representing initial angular momentum. And I omega 2 is representing final angular momentum. Take it to this side. It says I omega 1 equals I omega 2. Right? I omega 1 equals I omega 2. Which means total initial angular momentum equals total final angular momentum. See, more or less the same idea. Right? So having a thorough understanding, a solid knowledge on linear motion and linear momentum is very much advantageous when it comes to angular momentum. Right? Linear momentum angular momentum is nothing. Right? We are just adding up the things. But when you have a thorough knowledge, a solid knowledge on the linear momentum parts, we have covered around 3 months back. Doing this is very much easy and few parts will be added. Right. Now, as the conservation of linear momentum is stated as when there is no external unbalanced force acting on an object, total linear momentum is conserved. Right? So this is also very comparative. Only 2 words are going to change. When there is no external unbalanced torque acting on an object, total angular momentum is conserved. Right? Very comparative. Right? So that's the benefit, that's the advantage you have when your linear motion knowledge is solid. Right? Because I told you on the first day itself, angular motion is building upon linear motion. Right? That is like an extra mile, extra step, next step of a linear motion. Right? That is how it builds up. Okay, take down both. So this is what we need for now, but when you are studying, you can study with the comparison, that is easier, right? If you can keep in mind about one thing, the other one can be derived easily. Take it down. Take it down. By these two conditions, the system is in equilibrium. No, no, we can't say. Because if a system is in equilibrium, there are two other conditions to be satisfied. Right? We have discussed on the equilibrium of forces. Okay, write down below. Write down below the linear momentum side. I'll be giving you both to you to see the comparison, right? Then easily you can compare and contrast, and only two words are going to change, right? Only two words are going to change. Then easily you can keep that in mind, right? So in this side, write down linear momentum side. Write down linear momentum side. If there's no external unbalanced force, if there's no external unbalanced force, if there's no external unbalanced force, if there's no external unbalanced force acting on an object, if there's no external unbalanced force acting on an object, total linear momentum is conserved. 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 Right? Write down under angular momentum side using red. Write down under angular momentum side using red. Write down under angular momentum side using red. If there is no external unbalanced torque, if there is no external unbalanced torque, if there's no external unbalanced torque acting on an object, external unbalanced torque acting on an object, total angular momentum is conserved. Total angular momentum is conserved. total angular momentum is conserved, right? Okay, so that's about the comparison between linear momentum and angular momentum, right? About the conservation laws, right? Now write down below as a common point, right? I mean, this part is over. This part is over. Now write down below as a next point, not relevant to either side, right? As a common point, write down with a red pen, using a red pen. Angular momentum is a vector. Angular momentum is a vector. Next point. Angular momentum is a vector. Angular momentum is a vector. Next point. Next point. Its direction is same as. Its direction is same as. Its direction is same as. Its direction is same as the direction of. Its direction is same as the direction of. Its direction is same as the direction of angular velocity. Its direction is same as the direction of angular velocity. Right. How can we find the direction of angular velocity? How can we find the direction of angular velocity? We discussed that was also on the first day of angular motion. How did he find the direction of angular velocity? Right hand rule, right? So within brackets, write down direction is given by right hand rule. Within brackets, write down direction is given by right hand rule. 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 Okay. Right. So that's all about angular momentum we have as theories, right? About angular momentum. Now let's see what our application types are. I will explain the other things coming up by using application itself, right? Go to question 1, page number 2. Go to question 1, page number 2. Question 1. You can raise if any doubts. Question 1. A child is running along a tangential direction to a disk of radius capital R and moment of inertia capital I. Then he sat on point on the circumference immediately after getting on board of disk. Mass of child is simple m. Determine angular velocity omega of the disk when he is on board. Initially, disk is at rest. Okay. First, take this down. Take down the diagram. I'll explain this from scratch. This is a first question. No, this is the first question. So I'll explain everything from scratch. Take it down. Now this is a disk. This is a disk, and this child is running. Then this child is running with a velocity v. Along a tangential direction like this. The child is running with a velocity v to a tangential direction. Tangential direction means that is along a tangent. No, tangential direction is along a tangent, right? Now, if I draw a normal to a tangent, it goes to center. Or in other words, right, the opposite. If you connect the center with a tangent, right, with a tangent, it will always be perpendicular, right? So therefore, for sure, this is a right angle, right? This radius is given capital R, right? And the moment of inertia of the disk is given as I. Moment of inertia of the disk is given as I, right? Okay. And now this is our initial scenario. This is our initial scenario, right? Initial. In final scenario, what happens is the child is on board. The child is on board, right? So he will be onboarded to disk to the disk like this. He will be onboarded to the disk like this, right? And then it's going to create a motion for the disk. So let's say angular velocity of the disk that is obtaining, that is getting now is omega. Initially it says it is 0. So initially omega equals 0. Initially omega equals 0. This is our final scenario. This is our final scenario. Now it clearly says that mass of child is m, and the child is then he sat on the point. He sat on this point immediately once it's on board, which means now imagine what is happening. The disk is like this. This is a horizontal disk. This is a horizontal disk, and the child is running towards a tangential direction, and he is jumping on. He is getting onto the disk, and then once he is getting onto the disk starts to rotate, and the child is at rest at this point with respect to the disk. Now both are rotating. Right? So this is like a what we call a merry-go-round, something like that. Right? In some kindergarten play areas also, some of these things are there. Right? You might have seen, right? The seat with the seats and everything. Now if you jump onto a seat and if you stay there on the seat, it starts rotating, something like that. Now this is a disk. Okay, take it down. I didn't receive the route on the channel. Take it down quickly. There are quite a few things to do today, right? So I'll go a little bit faster. When it comes to our questions, angular momentum is a very popular part. When it comes to our questions, it's a popular part. Okay, look at here. Now first you have to make sure whether external torques are applied here. Right? There are no any external forces, no. Since there are no any external forces, there is no external torque. Right? Torque is the force moment about the point of rotation. No? There is no torque since there is no forces, no external forces. Right? Which means our angular momentum is applicable now. Right? This is how we apply. Look at the board. This is how we apply. So you have to write this. You have to say this by using law of conservation of angular momentum. Right? The idea here is total initial angular momentum equals total final angular momentum. Total initial angular momentum equals total final angular momentum. Right. Now, this is very much similar to what we did in linear momentum. Right. You have to apply angular momentum, right, one by one for objects. Exact same thing we did in linear momentum. Apply angular momentum I omega for the objects one by one. Right. Now, for your ease of understanding, let me write this way. Right. There are two objects of simple M and disk. Let's refer simple M as simple M. Then angular momentum of M plus angular momentum of disk equals. Finally, also we have two things: angular momentum of M plus angular momentum of disk, like this. So we know two ways of expanding angular momentum, either as I omega or as MVL, right? You have to pick the correct equation, correct in the sense relevant equation based on the availability of data. You have to pick the relevant equation based on the availability of data, right? So go to simple M, angular momentum of simple M. You are trying to write angular momentum of simple M. Moment of inertia of simple M is not given, but instead linear velocities are given. Since linear velocities are given, now you can go with this MVL. Then linear momentum is MV. Linear momentum is MV. Moment of linear momentum, MV into perpendicular distance. Perpendicular distance from rotational axis is exactly R. Perpendicular distance from rotational axis to linear momentum is along this line. No? Linear momentum is acting along this line. So the perpendicular distance is exactly R plus angular momentum of disk. Angular momentum of disk. I is given. I of disk is given. Right? There is I. But initially, omega is 0. But initially, omega is 0. Right? Let me put brackets for your understanding. Right. Then, in this side, we have final values. Final values. Right? Angular momentum of M. M. Now, M don't have any linear velocity. But he is sitting on the disk now. Then with the same angular velocity, both are rotating around. Because if the person is sitting on the disk, when this rotates, that child is also rotating with the same angular velocity. No? So he is on the disk. And for sure we can see, with respect to the child, this is an external axis. With respect to the child, this is an external axis. Right? This is an external axis. Then I can be written as mr squared at once. Right? I will do that expansion in two lines. Right? So here you can write this as moment of inertia of child into, right, moment of inertia of child into omega, plus for disk, moment of inertia of disk is given I into omega of disk, omega. Right? Now simplify this. This is MVR equals IM. This is about an external axis, no? If there is an external axis, you can easily expand this as how? MR square. If there is an external axis, you can easily expand this as MR squared. Then this can be expanded as MR squared. We just learned in moment of inertia. Right? Now omega is common. Take omega out. Right? We need omega. So omega of the motion is given by MVR over I plus MR squared. This is the new linear velocity. Sorry, this is the new angular velocity of the disk. Disk in the sense the system. Both child and the disk rotates with this angular velocity once this child is onboarded. Right? Right. Very much similar to the application of linear momentum. Very much same. Now here we have two options. You have to pick the correct equation when you are proceeding, when you go ahead with the availability of data. If moment of inertias are given, you can go that way. If linear velocities are given, you can go this way. Right? Raise your hand if it's clear, and the ones on YouTube also put to the chat if it is clear. Clear. Sansa, what about you? All good? Sahansa, are you also all good? Take it down. So if any questions, you can ask meanwhile. Yes, okay, good. Take it down, and if any doubts, if any questions, you can ask meanwhile and get it clarified. And one more thing, we have to mention the direction, right? I have considered this direction. This is a vector, right? Mention the direction of rotation you are considering here. Write down below with a red pen. Write down below with a red pen. First point. First point. Apply linear moment. Sorry. Apply angular momentum. Apply angular momentum. Apply angular momentum for each object separately. Apply angular momentum. Apply angular momentum for each object separately. Apply angular momentum for each object separately. Apply angular momentum for each object separately. For each object separately. When using law of conservation of angular momentum. When using law of conservation of angular momentum. When using law of conservation of angular momentum. Second point, keep using red. Second point, keep using red. Pick either I omega O MVL. Pick either I omega O MVL. Pick either I omega O MVL. Pick either I omega. Pick either I omega or MVL. Or MVL based on the availability of given data. 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 Right. Let's move on. Go to question 2. Go to question 2. Question 2. It says two children of masses capital M and simple m running with velocities v and u respectively along two tangential directions to a disk of radius simple r. It should be capital R, not simple r. It should be capital R. Correct it as capital R. Radius capital R and moment of inertia I. Moment of inertia I. Right? Moment of inertia I, not J. Right? Moment of inertia I. Initially, disk is at rest. Now two children get on board immediately at the same time and sit on the circumference. Determine the angular velocity of the system now. Okay. The diagram is also given, and it's given that MV, capital MV is greater than simple MU. Okay. Start working on the question. I will start the discussion in 2 minutes. You will receive all multitudes in another like 3 to 4 days. I mean, before next class, for sure you will receive. Sansa, you also please make sure that you have updated the correct living address on the website, because we will be taking the addresses from there, right? So please update it accordingly with your correct living address. That will be the same address the food delivery is done. You can send your answers if you got any. It's always better to have two scenarios, two diagrams for two scenarios. Then easily you can picture what is happening here. It is not on the channel. No, it's on the channel. On both. Check again. This is the initial scenario. Or if there's anyone else who has got the soft copy, right, through the channel, you can put it to the Zoom chat. That is fine. The set of the circumference, then simple m and capital M. Okay, any answers before I start? Any answers? R equals mv plus mu I plus. There's a tiny mistake. I know the reason. Check your directions again. Check your directions again. That's a small mistake. Put some more attention to the directions. Right, let's start. Okay, now let's assume this omega s. Now you have to decide this. You have to decide this. See, now it is given that mv is greater. If mv is greater, the moment created by mv is higher. Then because of that mv, higher mv, this rotates in this direction. So let's assume that as omega, right? This rotates in anti-clockwise direction. So it rotates this way. Right, this is final scenario. Final. Right, so let's apply using law of conservation of angular momentum. Right, total initial angular momentum. Now there are three objects. So apply one by one. Apply one by one. For this one, now let's specify the direction. Now this is the direction I'm going to use. Then for this one, capital M, that rotates in the same direction. It supports the momentum in the same direction, mv, right? And this supports in the opposite direction, minus mu, plus disk is at rest. So initial angular momentum is at is zero since that is at rest. Final one. There are three objects again. Three objects. Moment of inertia of simple m, right, into omega plus moment of inertia of capital M into omega plus moment of inertia of disk into omega, right? So what I have written here is P of capital M plus P of simple M plus P of disk. This is P of simple M, P of capital M plus P of disk, right? Then mv minus mu equals omega is common, take it out. Im about simple m, this is an external axis. For simple m, this is an external axis. So it can be written as m r squared, right? For capital M, this is an external axis again. So that is capital M r squared plus I. Subject omega from this, omega is capital M v minus simple mu over I plus r squared is common, simple m plus capital M. Final answer. Yeah, minus. Good. Am I missing R? Yes, yes. Sorry. MVR and MUR. Right? Final answer. Because angular momentum is a vector. It's a vector. All basic rules regarding vectors are applicable. All the basic rules regarding vectors are applicable. Right? All the basic rules regarding vectors are applicable. Write it down. If any changes, take it down. Write down below with a red pen. Write down below with a red pen. Angular momentum is a vector. 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 Hence, all basic rules. Hence, all basic rules. Hence, all basic rules regarding vectors. Hence, all basic rules regarding vectors are applicable. Hence, all basic rules regarding vectors are applicable. Right. Go to question 3. Go to question 3. It says an ant is at rest on the circumference of the disk of radius r, which is rotating with angular velocity omega naught. Now, the ant starts to move along the radial direction with a uniform velocity. Radial means along a radius. Along a radius. Right? Along a radius. With a uniform velocity v. Determine the angular velocity of the disk when the ant is d distance away from the center. Simple d distance away from the center. Mass of ant is simple mn. Moment of inertia of the disk around rotational axis is capital I. Okay. Start it. Question 3. Read the question carefully and start. Start question 3. Start question 3. Start question 3. I will start in 2 minutes. Send your answers if you got something. Ask if anything and get clarified. Right. Question 3. So both diagrams are given already. Both diagrams are given already. So initially, the ant is this ant is at the circumference. Initially, the ant is at the circumference. Simple r distance. Okay. Now this is given as omega naught. Simple r. Right. This is initial. And in the next scenario, our ant has walked towards the center. It has walked towards the center, and now at d distance away, and its moving velocity is v. We need to find new omega. So let's assume it as omega. V over d. No. Angular velocity of disk when d distance away from center, right? This is our final scenario. Omega naught I plus mr squared over omega naught I plus mr squared. Omega naught I plus mr squared. That's a possible answer. Good. That's a possible one. Right? We'll check. That's a possible one. Okay, right. Same logic. Using law of conservation of angular momentum. Using law of conservation of angular momentum. Using law of conservation of angular momentum. Right. Now we have two objects, right? Then there should be an angular momentum for ant and disk. Finally, also ant and disk. Right. So about ant here. For ant, this is an external axis. Right? For ant, there is an external axis, no? Then let's consider moment of inertia of ant at this point as IA. Right? IA. Then IA r squared. Sorry, let's write this way. IA omega naught plus PD. Fine. Angular momentum of disk. Moment of inertia of disk is given as I. Angular velocity is omega. So that is I omega. I omega naught. I omega naught. Right. Second scenario. Angular momentum of ant. Now ant is also rotating with this omega. Still ant is in an external axis, right? Still the ant is rotating about an external axis. Then we can write that as, let's say, this is IA dash. And the moment of inertia IA is IA and IA dash. And for this one, there is IA dash times this new omega plus for the disk, same I of the disk into omega. Tell me, this is the important thing here. Tell me, does this and create a moment due to linear momentum? Does this and create a moment due to linear momentum? Because if there's a moment of linear momentum, which means there is an angular momentum, then it should be factored here. Should be factored here. What do you say? Is there a moment of linear momentum due to this and MVL, moment of linear momentum? Yes or no? Yes or no? Quickly. Raise your hand if you say no. Raise your hand if you say no. Sarah says no. Arkham, yes. YouTube. Anyone on YouTube? Listen. The answer is no. The answer is no. The reason is this velocity goes through center. That is a radial direction. When velocity goes through center, that angular momentum, that linear momentum is radial. Linear momentum is radial. That is along the radius. So there is no perpendicular distance in between. Perpendicular distance is zero. So it doesn't create any moment of linear momentum. Doesn't create any. So that's it. IA can be written as what's the mass of the ant? Simple M. Then M R squared plus I, take this out, omega naught, right? IA dash is MD squared plus I, take this out. So we need omega. Omega equals omega naught times I plus MR squared, right? And this is I plus MD squared, right? So that is a moment. If a force goes through the considered point for force moments, no moment is coming from that force. So something like that. This MV goes through the point of rotation. No moment due to that MV. Right. So this is the final answer. Was that what you gave? Uh, omega naught. I think there's a bracket there. Yeah, your answer is correct. Good. Right. So I suppose there's a bracket. Right. So if the bracket is there, your answer is correct. Good. Take it down if anything. Right. right? Write down below with a red pen. Write down below with a red pen. Write down. No moment due to linear momentum of ant is created. No moment due to. No moment due to. No moment. No moment due to. No moment due to linear momentum. No moment due to linear momentum of ant. No moment due to linear momentum of ant is created. Is created since linear momentum goes through point of rotation. Since linear momentum goes through. Since linear momentum. Oh, within brackets velocity linear momentum within brackets velocity. Linear momentum within brackets velocity goes through point of rotation. Goes through point of rotation. Goes through point of rotation. And within brackets again. Within brackets again. Within brackets again. No perpendicular distance. 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 Right. Start question 4. Start question 4. Earth revolves around the sun in an elliptical path. Right. Prove that the angular velocity of Earth increases when distance between sun and Earth decreases, and angular velocity decreases when distance between sun and Earth increases. Right. So they are given as R1 and R2. You can assume omegas at 1 and 2 as omega 1 and omega 2, right? And somehow I have to prove that omega 2 is greater than omega 1. I have to prove that omega 2 is greater than omega 1, right? Use the same notations. I will help you out with the notations. So you also can follow my notations. That will be easy, right? So this is the sun, right? And this is the elliptical path of Earth, right? This elliptical path of Earth, right? And this is given as R2. This is given as R1, right? So assume omega, respective omega here as omega 2 and respective omega here as omega 1. So somehow we have to prove that omega 2 is greater than omega 1. Somehow we have to prove that omega 2 is greater than omega 1. First give it a try. Give it a try. Right. Anyone? It should be a logical one. Be a logical one. Na? Finally, we have to prove that omega 2 is greater than omega 1. And since this is an ellipse, one thing is given that this is an ellipse, no? Since there is an ellipse, for sure we know R1 is greater than R2 because of an ellipse, right? This is given, right? This is given. Not a circle, there is an ellipse. Not a circle, there is an ellipse. I will start in a minute. We will try a little bit different one from the previous questions we discussed. R squared omega is constant. It is correct. It is correct. So somehow you have to take that argument to an inequality, because if you have to show that omega 2 is greater, then somehow we have to prove it to an inequality, right? Right. Let's start. Okay. This is our first scenario. This is the second scenario. Right. Then using law of conservation of angular momentum, we can say if this is 1, I1 omega 1 equals I2 omega 2. No? Let's assume mass of Earth as m. That is a constant. Let's assume mass of Earth as m. That is a constant. Now, Earth rotates about an external axis. So I1 can be expanded as m1. I1 can be expanded as m1 r1 squared no, omega 1. I2 can be expanded as m1 m r1 squared. I2 is same m r2 squared omega 2. Like this, no? So even though it revolves, mass remains constant. Mass remains unchanged. Right? Then m to m cancels. Now we have something like this. R1 squared omega 1 equals R2 squared omega 2. Right? Since I have an inequality here, right? This is a given inequality for the ellipse. Right? If we are proving an inequality, listen, if you are proving an inequality, you have to start from an inequality and prove it. Right? If you are proving an inequality, if you need to get an inequality for the final answer, right? If you need to get an inequality for the final answer, right? If you need to get an inequality for the final answer, you have to start from an inequality and do some simplifications and reach the final answer. That's how. Otherwise, at the last step, you can't get the inequality out of nowhere. Always you have to start from a logical inequality. Now, this is the only inequality I have at this moment, right? At the moment, right? So therefore, I'm going to substitute something here. For that, let's subject R1. If I subject R1, see what is happening. R1 squared equals R2 squared omega 2 over omega 1. So R1 is R2 root omega 2 over omega 1. No? R2 root omega 2 over omega 1. Right? So let's plug it here. Right? So let me start from this. We know R1 is greater than R2. For R1, we can substitute R2 times root omega 2 over omega 1 greater than R2. Now R2 cancels from both sides. Right? And this is what remains now. Omega 2, omega 1. If this is cancelled, there is only 1. So square both sides. Square both sides. Then omega 2 over omega 1 is greater than 1 squared is still 1. Then it says omega 2 is greater than omega 1. Right? Final proof. Omega 2 is greater than omega 1. So likewise, we have to take it to the inequality starting with the non-inequality. Right? Using angular momentum, I got something for R1 and plug it here. See, now it says omega 2 is greater than omega 1. That's a proof. See, the question says, prove that. So prove that. So this is the proof. Now omega 2 is greater. Omega 2 is greater means when this gets closer, omega increases. When this gets far away, it decreases. Got it? Omega 2 is greater than omega 1. That is why, right, there are phenomena behind this. That is why sunset and sunrise changes time to time. Time to time in the sense in some time period of the year, we have longer daytimes. Like around 5:30 in the AM and until around 6:37 in the evening, around 7 in the evening, we have daytime for some periods of the year. And in some when it's get dark, right, when it gets dark, it will be around like 5:36. What difference at the end? Because for a country like Sri Lanka, since we are living close to equator, this impact is a little bit less. So that's why we have a slight difference. But when it comes to the other countries which are kind of far away from the equator, they experience like 18 hours of daytimes and only 6 hours of night time, something like that. Such countries are there with these changes. For us also, that is there, right? Our sunrise and sunset is never going to be like 6 a.m., 6 p.m. No, it changes. There are some periods of the year like we are getting the dark like fast in the sense around 6, around 5:36, all around is dark, right? When the daytime is shorter means we are traveling faster. That is when the earth is somewhere here. When the daytime is faster, which means earth travels slowly. So then that is somewhere here. So that happens throughout the year like that. Natural phenomena. Right, take it down. Okay, write down below with a red pen. Angular momentum is conserved. Angular momentum is conserved. Angular momentum is conserved. Angular momentum is conserved. Angular momentum is conserved when Earth revolves around Sun. When Earth revolves around Sun. when Earth revolves, when Earth revolves around Sun, when Earth revolves around Sun, since no, since no external torque, since no external torque, since no external torque acts on it, since no external torque acts on it. Next point, next point, write down. Start from, start from, start from a proper inequality, start from a proper slash valid के लिए, start from proper slash valid, start from proper slash valid inequality, start from proper slash valid inequality. If an inequality should be, 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 if an inequality should be derived as the final answer, if an inequality should be derived, if an inequality should be derived as the final answer, right? Okay, go to question 5. Start question 5. Side length of given cube is simple A and mass is m. It moves with a uniform velocity v and hits on a small obstacle, obstacle O. If moment of inertia around O of cube is 203 ma squared, determine angular velocity of cube just after the collision. Angular velocity of cube just after the collision. Okay, right. Give it a try. Give it a try. Okay, any answers before I start? That's the cube of side length A. Obstacle is O. Okay. Any answers? Anyone? Since angular velocity is given, sorry, moment of inertia is given, since moment of inertia is given, which means it is going to do a rotational motion once it is hit on the obstacle, right? That's possible, no? Because when it is hit on the obstacle, it can be rotated around the obstacle. That's why moment of inertia around the obstacle is given, which means it is going to rotate around the obstacle. That is going to rotate around the obstacle. Now, if you are drawing both scenarios, this is initial. And finally, something like this. It is rotating around this. Final should be something like this, isn't it? Right? Finally, something like this. Any answers before I start? See, now same thing. Using law of conservation of angular momentum. Right? Total initial angular momentum. There's only one object here. So initially we don't know I omega, but mass and V, mv is known. Since mv is known, we can go ahead as moment of linear momentum, no? Right? Then initially mv times, right? This moment is created by this height. That is not a, that is a over 2 now. A over 2 equals. Finally, I is given. So you can write it as I omega. Plug this I. mv a over 2 equals I 3 over 2 over 3 ma squared omega. We need omega, right? Angular velocity or omega. Then m2 m cancels, and 1 a2 a cancels. Subject omega is 3v over 4a. 3v over 4a. 3v over 4a, correct. Good. Yeah, good. 3v over 4a. So I have used the velocity at center of gravity. V. Then you have to write the height up to center of gravity. Right. That's comparatively a simple question. Write down below with a red pen. Linear momentum of center of gravity of object linear momentum of center of gravity of object is considered linear momentum of center of gravity of the object is considered linear momentum of center of gravity of object is considered linear momentum of center of gravity of object is considered, right? Question 5, sorry 6 ne? Go to question 6. Start question 6. Start question 6. A uniform rod is hung freely at point A. Another particle of mass simple m travels with a uniform velocity v and hits on the free end of the rod. It sticks to rod immediately after the collision. Sticks to rod. Right. Determine angular velocity of the system after the collision. Moment of inertia of rod around A is 103 ml square. Okay. Give it a try. 2 minutes again. Question 6. Right. So this is the initial scenario. Visual. Now, if you can manage with a single diagram, it is totally fine. It is totally up to you, right? I'm drawing both diagrams for all of you to understand what's happening here. Right? Otherwise, if you can manage with it, if you are confident that you can manage with the single diagram, the given diagram, that is fine. That is fine, right? Okay, now the final scenario is this sticks to this. This sticks to this, right? So once it is stick, you know, this will start rotating. This will start rotating. This is stick to this, and the system starts rotating with a velocity, let's say that is omega, right? Something like this. Something like this. 3V/4 4L. It's a possible value. Possible value, good. 3V/4 4L. Moment of inertia of the rod is given, right? See? So apply the same. Apply the same. This is final. This is final. Apply the same using law of conservation of angular momentum, right? So initially we can write this using I omega, but mv is given. Then about a, we can write this as mvl no equals. Finally, now there are two objects. Zero ekat malli inna. See, angular momentum of simple length plus angular momentum of rod. Finally, also angular momentum of simple length plus angular momentum of rod. Angular momentum of simple length. MV is given. So that is MVL. Rod is at rest initially. 0. Initially the rod is at rest. 0. Right. Then angular momentum of M after the collision. Right. After sticking, we can write it as IM into omega plus rod is I of rod is given. 103 ml squared. 103 ml squared omega. Right. But IM for this one is an external axis. So IM can be written as external axis. Point A is external for this one. Then ml squared. IM is ml squared because there is an external axis. Then this is MVL equals IM is ml squared. Omega is common, no? Take it out. Plus 1 over 3 ml squared omega. See now what happens? Ml squared is also common. Take everything out. MVL equals, right? ML squared omega is common now. This is 1 plus 1 over 3. 1 plus 1 over 3 remains. 1 M2, M cancels. L2, L cancels. V equals L omega. Right? L omega. 1 plus 1 over 3 is 4 over 3. Right? 4 over 3. We need omega, subject omega. 3V over 4L. 3V over 4L. 3V over 4L. Correct. Good. 3V over 4L. Correct. Yeah, Sarah, your answer is correct. It's good. It's correct and good. Right. Take it down. So likewise, we have to apply this accordingly. So as a theory part, this is a small part, but when it comes to questions, like frequently and popularly, questions are coming. Right. Take it down. Write down below with the red pen. Write down below with the red pen. Point A is an external point. Point A is an external point. Point A. Point A is an external point with respect to. Point A is an external point. Point A is an external point with respect to simple m. Like simple m particle with respect to simple m, right? Point A is an external point with respect to simple m, right? Okay. So is it only about these 6 questions? 6, right? Yeah. About these 6 questions we discussed so far. Is it clear? Or any questions? Is it clear enough? Raise your hand if it's clear. Or put a thumbs up at least. Okay. Others? Right. Let's move on. As a next heading, write down other applications of moment of inertia. Write down next heading. Other applications of moment of inertia. 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 Right. So under that, write down rotational chair. Rotational chair. Under that, write down rotational chair. Right. Listen. Rotational chair is a simple experiment we can do at home or in the school lab. Right. In the school lab, the best one is there with the frictionless scenarios. Otherwise, if you try to do this at home, possible up to some extent, certain extent, but due to the friction constraints we have, sometimes you might not get the best results, right? So therefore, this is in school labs, rotational chair, right? So this is what we do using rotational chair. It is something like this, right? Now on this chair, this is rotatable. This is rotatable. This chair is rotatable. Chair is rotatable. Now on this chair, a person is sitting like this. A person is sitting on the chair. A person is sitting, right? So when his hands are closer, now this is when hands are closer, taken closer, right? One scenario, and this is the same rotational chair, right? When his hands are spread out, right? Two scenarios when hands are close to body, right? Closer, close to body and stretched. Right. Now, this is what we can notice here. One example, one demonstration actually. One demonstration for angular momentum and one of the popular demonstrations. Right. This is when hands are close. When hands are close to body. Right. This is when hands are stretched. When hands are stretched. Right. We know, right? We know I equals mr squared, no? I equals mr squared, where r is distance to center of mass distribution, right? Now what happens is when hands are closer, when hands are closer, look at here, when hands are closer, mass distribution from the axis. Now, axis of rotation is this. Axis of rotation is this. This is a rotational chair, right? Rotatable chair. Rotational chair again, it's a rotatable chair. Person is sitting on the chair and doing this, right? Getting hands closer and stretching hands away from the body, right? Mass distribution here is comparatively less, but mass distribution here is comparatively higher when hands are stretched. When mass distribution increases, this R increases. No, let's label these two scenarios as A and B for our ease, right? A and B. So therefore, RA is greater than RB. No, let me write this way. So therefore, RA is greater than RB. Sorry, mass distribution is less. No, RA is less than RB. RA is less than RB, right? But when R increases, right, what happens is I increases. When R increases, I increases, right? So therefore, I can say, right, IA is less than IB because from this we know I equals MR squared. I equals MR squared, right? Right? But more things. There are more things. But I omega should be constant, no? Because according to conservation of linear momentum, that is conserved. So I omega should be conserved. I omega should be conserved. Then higher I means omega is comparatively lower because when I increases, omega decreases according to this, right? So therefore, we can say omega A is greater than omega B. Omega is greater than omega B. So likewise, we can argue and demonstrate this using the rotational chair here, right? We'll write this note. Don't write this part. First, take this down. Don't write this part. I will give this accordingly. Don't write this part. Take this down. Okay, write down below. Write down these arguments in red. First point, write down. When hands are stretched, write down. When hands are stretched, distribution of mass increases. 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 Distribution of mass increases. Okay. So write down this below that point. Write down this below that point like this. Okay, like this. Write this down. Write this down. Distance to center of mass distribution. Very important. Second point. Use the red pen. Keep using the red pen. According to law of conservation of angular momentum, 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 product of I omega is constant. 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 Hence, omega decreases when I increases. Hence, omega decreases when I increases. Hence, omega decreases when I increases. Take this down. Take this down. And below this, write down this way as well. Okay, write down this way as well. Right? I omega is constant. So always, because of this, I and omega are behaving in opposite manner. Okay, now go to question 8. Go to question 8. Go to question 8. Go to question 8. It says a disk of radius r, simple r, and ring of outer radius, simple r, outer radius, simple r. It should be simple r. Why it should be simple r. Correct it. A disk of radius r and a ring of outer radius, simple r, of same mass is given the same force to roll. Which object has a higher angular velocity after the same time interval? Okay, give it a try. So likewise, you have to do some argument. Do some argument like this and try to get it logically. Through a proper argument like this. A is a disk. Right? Like this. That's a disk. Radius is r. Right? Radius is r and its omega is given as omega 1. And this is a ring. This is A. And this one is a ring. ring. So in ring, mass is distributed only in this part, and this outer radius is given as r. So this is omega 2. Scenario B. Get it right? Okay, any answers? Now, from today, since whole angular motion is 100% completed, right? After today, since angular motion is 100% completed, uh, in a coming week, right? Most probably during this month, let's see, right? We'll be having a separate seminar on graph plotting, because here onwards, now you know quite a few things so far in mechanics, and the knowledge in graph plotting is very much important. For that, I'll be conducting a free session, free seminar for graph plotting techniques, right? That is not limited to mechanics, right? That will cover all the techniques and all the methods that we use for graph plotting in A-level physics here, right? For last batch also, I had a separate lesson for 26 batch. Now for your batch also, we'll be having a session as that, right? So somewhere around rotational motion and circular motion, usually I'm having it. So yeah, most probably during this month, we'll see whether we can allocate a time. So then we'll have that session as well. Keep that in mind. Okay, any answers? Final question is, which object has a higher angular velocity? Which object has a higher angular velocity? That's a final question. Right. Look at here. Again, you have to check this mass distribution. This mass is distributed from, now this is the point of rotation, right? From this point, this mass is distributed from here to here, right? Mass is distributed from this point to this. Then point of center of mass distribution is somewhere around the middle of this. Somewhere around the middle of this. Something like this. Right? Now in this case, mass is distributed only in this part from here to here. So point of mass distribution is somewhere in the middle of that distributed mass. That distributed mass. Right? Which means clearly we can see here, say this is a RA, and this is RB. RA is greater than, sorry, RA is less than RB, right? According to I equals MR squared, right? We know when R increases, I increases, which means IA is less than IB. right? But we know I omega is a constant. I omega is a constant. Then when I decreases, omega increases, which means omega is greater than omega b. Right? That's the final answer. So high angular velocity is with A. High angular velocity is with A. Take it out. So likewise, you can build up arguments. We can build up arguments. We can build up arguments based on this. Right? Omega is greater than omega b. The solid disk A has the higher. Yeah, it's correct. Good. A. Correct. Good. So likewise, we can build up arguments. Write it down. So meanwhile, I'll show you a demonstration as well. Right? So you can watch this here. The screen is visible, right? Watch this as well. This is a demonstration of this rotational jar that we just discussed, and I'll show you another demonstration after this. Right? Okay. First, watch this one. Is the sound audible?
We can demonstrate the conservation of angular momentum the same way a figure skater does by going into a tight spin. I'm not a very good skater, so I'll use this turntable and a pair of hammers. I'll hold them out at arm's length so I get nice large radius, and I'll set myself in a slow spin. I'm spinning around at a constant speed, and then I draw the hammers close.
Sound is audible.
To my body, right. And I spin around very rapidly.
Was it?
As soon as I move them out,
when hands are stretched,
I can repeat this
and
as
when
many
hands
times
are
as I want
when hands are
until the
stretched,
friction
moment of inertia increases.
turntable
Right? When moment of inertia increases, omega decreases. Do you need to watch it again? I will know. Oh, sorry, maybe. I play karana. Watch it again. Now he is keeping two hammers on the hands to increase.
We can demonstrate the conservation of angular momentum the same way a figure skater does by going into a tight spin.
Mass further.
I'm not a very good skater, so I'll use this turntable and a pair of hammers. I'll hold them out at arm's length so I get nice large radius, and I'll set myself in a slow spin. I'm spinning around at a constant speed, and then I draw the hammers close to my body, and I spin around very rapidly. Right? As soon as I move them out,
so likewise, we can see a very clear difference.
As many
That's a
times
demonstration.
as I want,
that's a proof of this.
Until the friction of the turntable stops me.
And watch this as well. This is also a good one.
This is a Hoberman sphere. You can expand it and contract it using this
so you
string.
Can see by adjusting
what I'm going to do is to use it to demonstrate the conservation of angular momentum.
Right? I will stay muted.
The axis, I'm going to rotate it about this vertical axis, and that axis is also denoted by the string that passes vertically through the sphere. We will note first that the moment of inertia in this expanded configuration is much larger than the moment of inertia in this contracted configuration. So what we can expect is that if we give it some angular momentum in the expanded high moment of inertia configuration, and then we contract it, its angular speed should increase. And sure enough, it's one of the most spectacular demonstrations, I think, of conservation of angular momentum.
Work today is broken. Every day.
Okay. Let's move on. Question 7. Question 7. In question 7, there's a small difference in the diagram. This is a square. One thing is this is a square. Right? This is a square. Side length is A. Right? And this is how these dotted lines are drawn. Should be drawn. And M is here. Simple M is here. Simple M is here. And cut off that Y part, that thing. Right? And this is how the rotational axis should be. Make the rotational axis. Right? Axis of rotation. Okay, make that change. Make that change. And go to question 7. The combined object is made of a plate of side length A and a small particle, simple M, attached to one vertex as shown. The total moment of inertia of the system is 7/2. Total is given as 7/2. Determine moment of inertia of the plate. Okay, first take this down. Okay, so what I'm going to use here is, from the definition, from the definition of moment of inertia, we know I total can be written as sum of I of each particle, no? Each object, each particle, use the same. So total I should be, total I of the system should be, I total can be written as I of simple M plus I of plate. Right? Plate is, tell me, plate is rotating around an own axis. So you can't write it using MR squared. But M is rotating around an external axis, which means we can write it using MR squared. Right? For plate, there is an internal axis, own axis, internal axis. Right? But for this one, there is an external axis. Right? Now I total is given. Now, but to write M, I need to know the perpendicular distance. No, perpendicular distance from here to here is this. So let's assume this as x. That I need to find out. Since this is a square, right? We know. See, since this is a square, we know these lines are intersected. Right? Diagonals are intersected normally, perpendicularly. Now M is here. Right? So easily we can find this out. You can easily find this out. Say this is x. If I draw a bisector here, right? This side is a over 2, no? Right? And since this is 90, this angle divides to 45. Easily we can write a trigonometric ratio as what about sine? Sine 45. If you write sine 45 is opposite side is a over 2 over hypotenuse x. So sine 45 is 1 over root 2 is a over 2x. A over 2x. Then simplify this. X equals this thing cancels a over root 2. So likewise, first you have to find what x is. X is a over root 2. Then easily we can apply that here. I total is given. What's the value? 7 over 2. Right? M can be written as mr squared. Now instead this is mx squared plus I will keep this as IP. Simplify. 7 over 2 ma squared is m x squared is a squared over 2 plus IP. Right? Then simplify. IP equals, take ma squared out, 7 over 2 minus half. Right? 7 over 2 minus half. So it says that is 3ma squared. So likewise, you can find the moment of inertia of an unknown one using other known moment of inertias as well. Right? Using our definition, because in the definition it says total is given by addition of each, sum of each. Right? Same thing. Take it down. So likewise, these other application types of moment of inertia is also coming. Not that frequent, not that popular, not that frequent, but it's also coming. So that's why I explained about these two as well before winding up. Take it down. Right? Okay, write down below with the red pen. Write down below with the red pen. Total moment of inertia is equal to total moment of inertia is equal to total moment of inertia. Total moment of inertia is equal to total moment of inertia is equal to the sum of is equal to the sum of all moments of inertia, sum of all moments of inertia of each object, sum of moments of inertia of each object about the same axis. Total moment of inertia is equal to the sum of moments of inertia of each object about the same axis. Right? Listen. Right, listen. So with that, we have come to the end of angular momentum as well, the 100% completion of angular motion or the rotational motion. Right, so this is the end of rotational motion as well. Right, with all theory parts and the questions, everything. Right. So next week, next week we are starting another very popular and a crucial part in our syllabus, because it is going to be highly connected to gravitational fields coming up, magnetic fields coming up, right? There are more things in there as well, right? So that is circular motion. Circular motion. Now we have completed rotational motion, and we are to start circular motion next week. We are to start circular motion next week, right? One of the most critical parts and very popular when it comes to questions, because there are many places in the syllabus we are going to use these theorems in circular motion, right? So we are starting circular motion next week, right? And that will be the main lesson to be covered during the month, circular motion. And after circular motion, we will be studying hydrostatics. Now we are moving towards the latter parts of mechanics, right? After circular motion, we have only two left: hydrostatics and hydrodynamics, right? Only two, right? So those are the things, and you will receive all your tudes before the next class, right? In about circular motion and all, we will reserve it before the next class, right? And as I told you, the graph plotting seminar will also be having most probably during the month, right? Let's say now today is only 7th, right? Sorry, today is 9th. Sorry, 6th of February. Today is 6th, right? So most probably we'll have during the month. That I'll inform. You can get all updates through the channels, right? Through the channels and in your groups as well. All right then. Any other questions? Anything to know? Any other questions or anything to clarify before winding up? Is there anything? No? Is it all clear? Right. Good. So if no questions, we will wind up. If no questions, we will wind up. And there is a clear drop in live participation to this class. I have noticed for like 2-3 weeks, right? For 2-3 weeks, right? So I highly encourage you to be in the live class. So if you are not participating in the live class, I will think again about the duration that I am keeping the recording on the website, right? That I will see. So providing recording is a benefit you have. No, that's an advantage. That's a benefit you have. So don't lose that benefit. Don't lose the benefit, right? Otherwise, if I feel like you are not participating in the live class and always going to go through the recording, right? Always going to go through the recording without being on the live class, without being in the live class, right? Probably I will shorten the time that I am keeping the recording on the website, right? Okay, keep that in mind and be mindful on that, and always try to be in the live class if there is not a unavoidable reason, not a reasonable reason, not an unavoidable or reasonable reason, right? Okay then, right? If no any questions, we will line up. And today we will be having the next S2A discussion at 8 p.m. Right? We'll be starting our S2A discussion at 8. Right? So see you there. And if you are not joining the S2A, we will see you again in the next class. Right? All right then. Then if no questions, we'll line up. Study hard and stay safe. Right? Good night and goodbye. See you.